doing this a little bit more formally. So we're going to represent our signal as an infinite weighted sum of an infinite number of sinusoids. So the Fourier transform, here it is in its beautiful glory in one dimension, okay? F of u is the Fourier transform. We just take the infinite integral of the original function times e to the minus I 2 pi ux. And you might say, what? Where did that e to the minus I blah, 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 come from?
Where did that come from?
Oh, she didn't fall into that trap. Well, again, remember from your probably calculus class somewhere, e to the ik is cosine k plus I sine k. That's why this is the even part and that's the odd part. This is where I is square root of minus 1. By the way, if there are any electrical engineers out there, they have j as being the square root of minus 1. I don't know why, because mathematicians use I. I guess electrical engineers didn't like the mathematicians. We're going to use I. So what the Fourier transform does is it converts from the spatial domain into the frequency domain. And the frequency domain is either written as omega, sometimes as u, as we're doing here, sometimes even s when you're talking about Laplace transforms and stuff like that. But the idea is that this cap f is the frequency spectrum, or I should say its frequency of f of omega. And we're going to talk about its magnitude in a minute, which is going to be sort of what when we refer to as the spectrum. Just for completeness, by the way, so here we had the Fourier transform. This is the inverse Fourier transform. Unsurprisingly, if you tell me what all of the sinusoids are, if I sum them all up, okay, at some location x, and I sum up over all the sinusoids, I can recover the original signal. And that's called the inverse Fourier transform.